Hi there guys, and first off let me just start by saying thanks for everyone for attending this session today. So today what we're going to do is take a look at how SOLIDWORKS Simulation can be leveraged in order to not only validate our designs but also optimize them before going even further in order to ensure that our design is going to last its expected lifetime. Now just before we jump into that, I want to start off by introducing myself. So my name's Kieran and I'm one of the elite application engineers here at TMS, which is a reseller based out of Scotland. Just a little bit about myself. Well, I've worked for TMS for almost 4.5 years now, and my main role is to provide both training and tech support to our customers. Now for that I cover a range of the SOLIDWORKS products, but simulation is one of the main ones that I cover. But that's enough about myself. So let's take a dive in and have a look at what we're covering today. Well, what we're going to do is we're going to have a look at this design. In this case, we're going to look at this pillar drill that we can see on screen here. And we're going to take one of the components of this design. And as we said, we're going to go through, first of all, carrying out a little validation of the design. Making sure, is it going to pass? Is it going to be able to withstand the loads that it's going to endure during its lifetime? Once we've done that, we're then going to look at how can we optimize that design. If it's failing, how can we make it better? If it's over-designed, where can we cut back on some material? And essentially, save money, one of the key goals. And finally, once we've went through that stage, we're then going to look at validating the life of the design. Now, sure enough, this pillar drill is not just a one-use product. You'd want to use it time and time again. So I need to ensure that all of the components of this design are built to withstand that repetitive loading cycle that it's going to go through. And that's exactly what we're going to do with our final analysis. So with that said, what we'll do is we'll jump on over to SOLIDWORKS here, guys. And as you can see, we have that very pillar drill on screen. Now, in actual fact, the part that we're going to look at here is this little handle that we can see down here. This little crank handle. Now, although it may be considered one of the smaller parts of the design, every component within this design is as valuable as the next. If one of these parts fails, the entire design fails. So we need to make sure that every component is up to scratch. So with that said, we're then going to jump on over into this little handle that we have here. And this is where we can get to work on carrying out our first validation analysis. So we're going to start off by creating a new simple study. We'll go for a static analysis in this case, and I can even give this a name. From there, when it comes to using SOLIDWORKS Simulation, it's nice and simple. It's all based off this tree structure that we have on the left-hand side. So we can simply go through one component at a time in order to set this up. Starting off with the component itself, where I can then come through and either pick out a material from my favourites library, or I can even get access to the entire SOLIDWORKS materials database. Now, for those of you that use SOLIDWORKS at the moment, you'll probably be familiar with this materials database. But in actual fact, what you may not have realised is that as we go through this materials database, it's actually got all of the material properties along with it within there. So I can then see exactly what properties are going to be used within my analysis. Now, as you can see, there's a number of different categories which are in here by default. But if the material that you're looking for isn't in there, there's no need to worry. Because sure enough, we can also create our own custom materials within there as well, where we can add in our own custom properties, which we may have got through testing of specimens, things like that. Or what we're going to do in this case is I'm going to stick with this 304 steel that we have. So I can click apply on it, close, and sure enough, I get a visual cue to say that that material has now been applied to my component. Next up, how's this component going to be restrained? Well, in this scenario, what I'm going to say is this little crank handle it's actually got a little bit stuck. Now, when we design anything, we always need to consider the worst case scenario. So the worst case for this little crank handle is that it's completely stuck in place. You're trying to turn it and it just won't move. So that's exactly what we're going to simulate. So all I need to do is simply right click on my fixtures from the tree and I'm going to add in some fixed geometry. However, we'll see there's a vast range of different fixtures that we can apply within there to suit all needs required. Now, another nice little thing about when we're applying any fixtures or even our loads within SOLIDWORKS Simulation is we get this nice little animation up here at the top as well, showing you exactly what that tool is going to do. In this case, it's showing this little fixed face, and if that was to be fixed in place and a load was applied to the component, we can see how it's unable to move. So that's exactly what we're going to do. Simply look at our model and select the faces that we want to restrain in place directly from the graphics area. From there, I can then click OK to my command, and I've now got my new fixture added into my tree here. To keep things nice and neat, I could also rename these features as well as I go along. So I can now say that those are my fixed faces. Next up, I need to apply my loads. So how is the load being applied to this little handle? Well, again, just a simple right-hand click, selecting the appropriate load that we want to apply. In this case, we'll go with a standard force. And again, from the graphics area, simply select the face that we want to apply it to. The only difference this time, guys, is I'm going to use this selected direction option, where I can then make use of some reference geometry. I'll use my front plane this time. And I can then say exactly which direction I want this load to be applied to. And again, we get the little graphical cues in my graphics area to highlight exactly which direction this load is being applied. I can then wrap this up by simply applying the magnitude of the load that I want. So we go for 320 newtons in this case. Click OK on it. And again, my load is now applied. And I get a visual representation from my tree as well. Just like my fixture again, I can come in and rename this, where I can then give this a name. In this case, I'll just call it load. Finally, the last step that I need to carry out before I solve this analysis is I need to go through this meshing stage. Now for this mesh, it's basically where SOLIDWORKS is able to go through and break the model up into loads of little elements. That's where it gets its finite element analysis. That's where that comes from. So once I've broken it down into those different elements, it's then able to carry out all the calculations on those elements in the background, saving you a little bit of headache of doing it all on paper, I guess. And we're then able to view the results. And just like that, again, we get a visual overlay of that mesh applied to my model. So I can see how that's starting to tie in with the model as well. Last step, I just need to hit run. And just like that, we've went through a nice, simple setup of an analysis, applying our material, fixtures and loads, applying our finite element mesh, and all of a sudden we've got some results right in front of us to work with. Now, when it comes to results, how can we process this? How does it work? Well, it's nice and simple, because what we have is this coloured contours which is applied directly onto the 3D model itself, along with this chart on the right hand side, where I can then see any colours which are yellow, orange or red are above my yield strength here, which again is nice and conveniently indicated on the chart itself. However, maybe I'm not interested in where in this region it lies. If it's above the yield strength, then that's all I need to know. Well, that's simple, because what I can do is simply select this value at the top of my tree, and I can change that value to be the yield strength instead. So I can type in the new value that I want to be my maximum of the chart. In this case, we'll go with the exact yield strength. Click enter on it. and it then updates my chart along with the contours of my model. So I can now see anywhere highlighted in red is currently the locations which are failing within my design. Not only that, I can then also look to add some little annotations within here. Maybe it's not so obvious where my maximum stress is. We get a nice little cue for that as well. Once I've finished processing my results of having my maximum value as the yield strength, maybe I want to set that back. Well, again, it's just a click of a button away, and all of a sudden, the chart's back to the way it started. So it makes it nice and easy to understand exactly what's going on. Now, another nice little step that I like to do when it comes to validating my setup for the analysis is it's always easier to understand if we can animate this out. So again, I can simply right-click on the plot that I'm currently looking at, click Animate, and I can maybe slow that down a little bit to see exactly what's going on. So I can see what's happening as that load's been applied. Now, looking at that, it looks like my setup's spot on. It's working the exact way that I thought it would. But maybe I want to share this with one of my colleagues as well. Well, again, that's nice and simple within SOLIDWORKS, because what we get is the option to save this to a simple AVI file. Because maybe my colleague doesn't actually have SOLIDWORKS Simulation, so how can they view this? Well, a little media file solves the problem. Next up from there, this is having a look at my von Mises stresses. And that's what's going to be plotted by default when we run an analysis. But we also have some other plots within here where we can have a look at our displacements. Again, works in the exact same fashion where we have our coloured contours and our plots. And likewise, we have our strain within there as well. So going back to my stress plot here, as we saw, this design is currently failing at the moment. If I use this load with this material, it's not going to work. So how do I know where to start changing my design? Well, sure enough, I can see my maximum stresses in this location, but to get a better understanding of where the load is having the biggest impact, what we get the option to do is to create a plot, which is called this design insight plot. Where I can then come in here, use this little slider in order to look at the percentage of the load and see where exactly it's impacting the most as I drag this along. So I can now see as I'm dragging this along, click OK on it to accept the changes that I've got. The load's having its biggest impact on this underside edge, but also across the thickness of this arm that we have as well. So that's where I want to start with my design change. I want to change the thickness of this arm that we have. Now for that, the first thing that I need to do is I need to set up some kind of variable within there. The variable that I'm interested in, of course, the thickness of that arm that I just mentioned. So the way that I'm going to do this is I'm going to create a new study within here. I'm going to create a design study. And within there, I can then set up that variable that I was talking about, where I can then add in a new parameter, where I can select exactly what I'm looking for within there. In this case, I've already got that parameter set up for me by simply just selecting the dimension out of my graphics area and adding that in. Now that I've got that variable in there, I can then specify how I want to change that variable. So okay, I know that 6mm is failing at the moment, so we don't want to go any less than that. But I can say that maybe I want to test, okay, maybe what happens if we go up to 10mm? But I'm interested in what happens between those two values as well. So we'll add in a step increment of say 0.5 millimeter. So what we're going to do is run a scenario going from 6mm to 10mm with 0.5mm increments as we go along. Once I've got my variable set, the next thing I want to do is set up what is it that I'm interested in. Well, the way we do that is by adding in what we call a sensor. In this case, I'm going to go for a stress sensor, looking at the overall stress within my model. From there, I'm then going to say, okay, I'm interested in the stress being less than a specific value. And this is where I can add in the exact value that I'm interested in. So in our case, it's round about 200 megapascals. That was the yield strength that we're looking at. Finally, I can then click over to my table view, and I can then see those 0.5mm increments that I have set within there. All that's left to do is click run on this. And what you could do at this point while it runs through each of these scenarios is go and pop the kettle on. By the time you come back, the results are right in front of you. Now, in this case, guys, you are going to need to make that a metaphorical cuppa, because in this case, we have sped this up a little bit, albeit it really is a fast process to go through. And the best part about it is, it takes out that mind-numbing task of you manually going through and changing the value and rerun the analysis. So it's a great little tool to use. Now, with that said, we then have our results presented in front of us in tabular form. Not only that, because of the criteria that we set up for that maximum stress to be below the yield strength, even gives me some visual representations from each of these scenarios to show me which ones are failing and which ones are passing that scenario. So in this case, I can clearly see that between 6 and 7.5mm, it's not meeting the criteria that I've set. However, from 8mm thicker, it's now meeting that criteria where we can clearly see that this is below that 200 megapascal limit that we set. Now, another nice little thing to know about this is we can simply click on the scenario of interest. Say we go for our first scenario that's passing our criteria. We can then dig down into those stress results in order to see exactly what's happening within there. Again, we get the contours on our model along with the chart on the right hand side. But that's looking at one scenario at a time. Maybe I'm interested in trends of what's actually happening as I change this thickness. Well, again, SOLIDWORKS makes this nice and simple by being able to define a design history graph. Within here, I can then say, okay, I want to plot my stress against each of the scenarios that I have, where I can then see this little chart showing how that stress changes for each scenario as it starts to get a little bit thicker each time. This then allows us to have a more informed insight into the decisions that we need to make. At what point are you making a model thicker than it needs to be, where it's having no effect on the stresses? At what point, effectively, are you over-engineering your designs? And essentially, at that point, simply just adding more money for the sake of it. So through this process, we can start to streamline those designs. In this case, I can see that 8mm is passing the criteria that I've set. So that's the one I want to go with. So again, I'm just going to make sure I've selected that scenario from my table. And popping back to that validate study that we created, I can then look into those results a little bit further to see exactly what's going on with it. I'm just going to rerun the analysis to update those results. And then we can get to work on it. Now again, it's just going to take a little second as it goes through processing this here. We can see just how quick that happens. And there we have our new updated results. Sure enough, we've got all the same plots that we saw last time round, but we've also got some additional tools that we can use as well. Starting off, we can have a little look at values at specific areas. Maybe I'm interested in picking out specific values, maybe around about this fillet area. Well, it's just a case of using my probe tool, selecting the areas of interest, and I can then pull out the exact stresses at those areas. I can also dig down into other values as well. Again, I can either use my right hand click, or a nice little one to know, guys, for you guys that are used to using SOLIDWORKS or the SOLIDWORKS S key shortcut bar. In actual fact, is fully customizable for simulation as well, where we can add in the tools that we want. In this case, I'm going to go for ISO clipping, where again I can type in a specific value of interest, and I can have it only show the values above or below that value that I've set. So again, we can start to dig down and see exactly what's happening at what location. Now, once we've went through processing our results and we're happy with our design, quite often we'll want to document this away. Now, that's usually when it gets to that daunting task of going through, right, okay, how did I set the model up? What's the properties that I've used for the material? What meshing parameters have I used? Well, instead of having to do that every single time, what we can actually do within SOLIDWORKS is use this report command, where we can have it set up so it's pulling out all of the information that we require, where we can simply toggle on and off bits that we're interested in. We can even add in some header information, whether you want the designer name, company name, logos, and we can have SOLIDWORKS automatically publish this for us. Now again, just to save a little bit of time here today, guys, I've went ahead and done that ahead of time. But what we get is this little document here, where we can see it's pulled out some images within here. It's even automatically created a table of contents. And as I scroll through, I can actually see it's pulled out key bits of information for me. Information about the model itself, information about the study. It's even pulled through those material properties automatically for me, along with our loads, fixtures, mesh, and most importantly, the results that we got at the end. So I can now see exactly what's going on within this model. Now, of course, it's not going to do absolutely everything for you guys. You still need to add in things like your assumptions, your introductions, your conclusions. But I'm sure you'll agree this is a huge time saver within there. So we no longer need to go through taking those screenshots, pulling out all those bits of information that it can do automatically for us. But jumping back into SOLIDWORKS, we've now completed the first two stages of the process that we spoke about. We've went through trying to validate our initial design, where it actually looked like it was failing to begin with. We then went through and optimised our design. So we've now increased the thickness of that arm to 8mm. Now, sure enough, that's great. It looks like it's going to work. However, we've only analysed this for one loading cycle. As we mentioned, this pillar drill is going to get used time and time again. This little crank handle, it's going to be adjusted multiple times. So how do I know it's going to withstand its expected life? Well, that's nice and simple through the use of what we call a fatigue study. Within here, it's a simple case of coming in, adding in a simple event that we want to run. In this case, I'll say we want to have 10,000 cycles. I can say whether this can be fully reversible, the load, so the load can be applied in both directions, or maybe it's just an on-off load, where it's being applied in a single direction. I can then pick up the study that I want to define that against, that validate study. So again, using that S key shortcut bar, I can simply select to run that study. So there's great ways of speeding up that process as well, especially if it's tools that you're already used to using. So once that's solved, again, nice and quick solution on it. But what do we get from it? Well, the first plot that we get out here is our damage report. We'll indicate exactly how damaged is this component after those 10,000 cycles that we've ran it for. In this case, it looks about 25%. Now, for anyone that finds it a little bit unconventional reading this as scientific figures, there's no need to worry about that. Because again, within SOLIDWORKS, what we can do is simply pop into the properties within here, and we can change our values as and when we need to. In actual fact, we can set this up within our templates as well, so it's set to that every single time we use it. So rotating this round, I can see that I have a damage of round about 25% within there. But how many cycles could it withstand? Well, that's where this next plot comes into play, where we can see the life expectancy of these locations. And sure enough, the minimum is set to round about 40,000 cycles. So it's well above the 10,000 that we set. So as we've seen through the combination of the different studies that we carried out, through our initial validation to see whether our part will pass or fail, through the optimization of the design using design studies in order to change the thickness of the arm, and finally through that fatigue study in order to validate the life of the design itself, we can see how we can now make more informed decisions in order to drive the design. And we've not even created a single prototype up until this point. So it's a huge cost saver right off the bat. Now, that brings me to the end of my little presentation here today, guys. So again, I would like to thank you all for joining us today, and I hope you guys have enjoyed it. If anyone would like some more information or has any questions about anything that I've went through, please do get in touch with us. Again, thanks for joining us today, guys, and I hope you have a great day.